Hello! First, I would like to thank the organizers of AofA for organizing this series of online talks. I will talk about a joint work with Éric, Fusy and Kilian Raschel on polyharmonic functions and random walks in cones. So first, let me motivate our work by recalling a few facts on harmonic functions. So let's consider a random walk in ZD with step set S and confined in some cone K. Denote by qxyn the number of excursions of length n between x and y and staying in K. By a result of Denisov and Wartel in 2015, we have an equivalent as n goes to infinity of qx0n given by v0 of x times gamma to the power n times m to the power minus alpha 0. Gamma and alpha 0 are explicit constants. Gamma depends on the walk, and alpha 0 depends on the dimension and on k. And v0 is a positive function which depends only on x. By considering the recursive relation for qx0n, which is qx0n plus 1 is equal to the sum over the possible steps s of qx plus s0n, and plug in the previous equivalent into this relation, letting n goes to infinity, we obtain that v0 of x is equal to 1 over gamma times the sum over s of v0 of x plus s. This implies that v0 is a harmonic function for the discrete Laplacian defined by this formula. Lf of x is equal to 1 over gamma the sum over s of f of x plus s minus f of x, and harmonic means that Lv0 is equal to 0. For example, let us consider the simple random walk in the quarter plane. So the steps are west, north, east and south, and the cone is a quarter plane. The number of n-length excursions qij0n is known by a result of Bousquet-Milou, so it is given by the following expression. And using Stirling formula, one obtains the equivalent as n goes to infinity of qij0n. So it is equivalent to 4 over pi times 4 to the power n times v0ij over n to the power 3. v0ij is equal to I plus 1 times j plus 1 and is a well-known unique up to multiplicative constants harmonic function positive within the quarter plane with Dirichlet boundary conditions. Our aim is to study more precise estimates than the first-order equivalent and to consider a complete asymptotic expansion of the number of excursions. If one has such an expansion, then using the same idea than previously, one can prove that the functions Vp, which appear in the expansion of are polyharmonic, that is, they cancel some power of the Laplacian, so L to the power k Vp is equal to 0 for some k. A few techniques may be used to obtain such an expansion, for instance, the Laplace method, the saddle point method, or analytic combinatorics in several variables. We'll see an example of such an expansion for the diagonal walk. On the other hand, the functional equation approach has proved to be fruitful when studying random walks problems. We'll see in the sequel an implementation of this method to construct biharmonic functions. So let us see an example of such a complete asymptotic expansion. So consider the diagonal walk in the quarter plane. The steps are northwest, northeast, southwest and southeast. The cone is again the quarter plane. So this is the most simple example since projecting the walk onto both coordinate axes gives two decoupled prefixes of dict path, that is one-dimensional positive walks. Hence, a simple application of the reflection principle gives an exact count for the number of n-length excursions, qij0n, given by this formula. Now using an integral representation of the binomial coefficient and applying the Laplace method to this integral, give the following result. So qij0n admits the following expansion. Here Vp is a polynomial of degree 2p plus 2, which is polyharmonic of order p plus 1 for for the Laplacian associated to the diagonal walk. So we have L to the power p plus 1 Vp is equal to 0. Note that, of course, polynomials are polyharmonic, since applying the Laplacian to a polynomial causes the degree to drop by 2. Vp is explicit. It is given in terms of Bell polynomials, and I have listed here the first terms. So V0 is again the unique positive harmonic function, V1 is biharmonic, V2 is triharmonic, etc. Now we will see how the functional equation approach can be used to construct polyharmonic functions. The general model of walks that we will consider are random walks in the quarter plane with small steps. Pij are the transition probabilities to the 8 neighbors, p00 is equal to 0. To avoid degenerated cases, we suppose that there are no 3 consecutive zeros in this list of probabilities, and we assume that the drifts in both directions are 0. The Markov operator of the walk is defined by Pf of xy is equal to the sum over ij of Pij f of x plus I y plus j, and the Laplace operator is defined by L is equal to P minus identity. So for example, we have the diagonal walk, the simple random walk, but also the tandem walk. So we will see more on this example later. And note that walks with small steps have been classified, and it is well known that there are 79 models of interest among the 2 to the power 8 different models of walks with small steps. Let us recall the functional equation method in the harmonic case. It was used in Raschel in 2014 to construct harmonic functions. So let h be a harmonic function, that is LH is equal to 0, with generic function capital H. An important quantity is the polynomial k, which is called the kernel of the walk. Now the harmonic equation LH is equal to 0 yields the following equation known as a functional equation for H. There exist many problems that can be reduced to solving functional equation. This equation has the advantage that in the right-hand side, involved functions depend only on one variable. To solve the functional equation, we have to introduce boundary value problems. And we'll first prove that h of x0, and in the same way h of 0y, satisfies a boundary value problem. That is, there exists a domain Gx in which h of x0 satisfies the following. So it is analytic in Gx, and also continuous on the boundary except at 1. And for all x in the boundary of Gx except at 1, h of x0 satisfies the boundary equation, which is that the value of kh at x0 is equal to the value of kh at conjugate x0. So here is a picture of an example of the domain Gx. And for an extensive treatment of boundary value problems, one can consult the famous Yellow Book by Fayol, Yanogorowski and Malishev. Let us now recall the steps in the method used by Raschel to construct harmonic functions. First, write the kernel as a second-order polynomial. And consider the solution expressed in x minus of k of x of y is equal to 0. Note that the domain Gx is an open set bounded by a certain curve defined by x plus and x minus. Now plug the roots x plus and x minus into the functional equation. The left-hand side is a 0, and taking the difference of the two equations leads to the boundary equation. Then one can solve the BVP to obtain that k of x0 h x0 can be written as an analytic function p of omega of x, where omega is an explicit conformal mapping in Gx. And lastly, you do the same for h0y, and by using again the functional equation, one obtains h of xy from h x0 and h0y. Thus, one of the results of Raschel is that for any polynomial p, the function h of xy equal to p of omega of x minus p of omega of x plus of x over the kernel is the generating function of a harmonic function. One recovers the harmonic function h from its generative function by the use of Cauchy's formula. Let us give two examples. For the simple random walk, choosing p of degree 1 gives that h of x and y is equal to 1 over 1 minus x to the square times 1 minus y to the square, which is the generating function of the unique positive harmonic function v0ij equal to I plus 1 times j plus 1. For the tandem walk, which is a walk with steps north, west, east and south, choosing again p of degree 1 gives that h of x and y is equal to 1 minus xy over x minus 1 to the power 3 times y minus 1 to the power 3, which is again the generating function of the unique positive harmonic function v0 for the tandem walk. So now we apply the method of Raschel to construct biharmonic functions for random walks. So let v be a biharmonic function such that Lv is equal to h, where h is harmonic. So applying the Laplacian again gives that L to the power 2 v is equal to 0, so v is biharmonic. This equation leads now to the following functional equation for the generating function of v. So it is similar to the previous functional equation, but there is an additional term given by minus xy times h of x and y. Plug in again the roots of the kernel into these functional equations leads this time to the boundary equation written here. So now we have a boundary equation for v, which is not homogeneous, the right-hand side being in general non-zero. Note that there exists general methods to solve this kind of equation, leading to some contour integral expression for v, but the resolution can be made easier in some particular cases. If the right-hand side is 0, the previous method works. It is the case, for instance, for the simple random walk. Or if the right-hand side can be decoupled. We will see what it means in the example of the tandem walk. So first example, the simple random walk. So here I have recalled the results of Raschel, so the expression for the kernel, the conformal mapping, and the general expression for h, the generating function of a harmonic function. Resolving the boundary equation for v, the generating function of a biharmonic function, gives that for any polynomials p and q, this expression is the generating function of a biharmonic function. Note that in this expression, h depends on p. So one can play with p and q to construct biharmonic functions, and if one chooses p and q as these formulas, one gets the biharmonic function v1, which appears in the asymptotic expansion of the number of excursions. Second example, the tandem walk. As said before, it is a walk with steps northwest, east and south. By Bousquet-Melou and Mishna in 2010, the number of n-length excursions is explicitly known. Here are the results of Raschel, so the expression for the kernel, the conformal mapping, and the general expression for the generating function of a harmonic function. And now we introduce the following function f, called the decoupling function. So f of x is equal to minus x to the power 3 over 1 minus x to the power 6. Defining g of x to be 3 times f of x times p prime of omega of x, the boundary equation can be decoupled, that is, the right-hand side is given by g of x plus of y minus g of x minus of y. As such, one can solve the boundary equation as previously, this time for the function kv minus g. This leads to the following expression for the generating function of a biharmonic function. So again, one can play with p and q, and for instance, one obtains the biharmonic function v1 which appears when doing an asymptotic expansion of Qij0n, starting from the exact counting given by Busquemelu and Mishna. Let us conclude by a few comments. So we plan to deeply investigate harmonic functions and their relation to complete asymptotic expansion of counting of works. Note that recursively one can construct polyharmonic functions of any order via the functional equation approach, but computations become a bit tedious. One crucial point to solve the tandem walk case was to guess the decoupling function, so we should understand and classify in which cases the boundary equation can be decoupled. There is a Brownian motion counterpart, so one can expand the directly hit kernel in terms of polyharmonic functions for the usual Laplacian. The functional equation approach also works in this continuous setting. And there are a few examples of works which arise from the representation theory of Lie groups. So for example, the tandem work is related to the special unitary group SU3. In these cases, the unique positive harmonic function is given by the dimension function of irreducible representations. It will be interesting to have a representation theory interpretation of polyharmonic functions. So here are a few references. So thanks for listening, and feel free to ask me a question by email.